already said, I'm going to talk about BSE at GW, and I'm going to tell you a little bit about what you can do with it in your research. And my talk, this webinar, will be very, let's say, hands-on. So I'm going to talk a little bit about the formalism, but not too much, maybe around 15 minutes, and basically tell you also in this presentation what you can actually do with these methods in ADF, what you can calculate, and then I'm just going to demo a few calculations. Before I start, I would just like to acknowledge a few people. So, of course, my PhD supervisor, Luke Fisher, with whom I developed most of those methods, and of course the NWO for funding, and also some of my colleagues at SCM who are now currently working in this field. So I guess these days we are quite active in there. So Eric, Pierre, Eduardo, and I, we are all kind of working on several aspects of these methods. So what is it all about? Let's talk a little bit about theoretical spectroscopy, right? So in general, we have a system which we kind of picture as an ensemble of non-interacting electrons, which are renormalized. So the interactions are kind of incorporated in the single particles. We call those quasi-particles. And two typical experiments which are very relevant in practice are, for instance, direct photoemission, where an excited electron actually leaves the system. So we basically turn our n electron state into an n-1 electron state. But then we have also photoabsorption, where we promote our system to an excited state. So the excited electron stays in the system, and the excited electron is bound to other electrons in the system by Coulomb interactions, right? And this problem is actually more difficult than the first one, because direct photoemission, that just requires us to look at one particle, but photoabsorption requires us to look at two particles, electron and a hole. And well, you all know about TDDFT, I assume, and BSE is actually very similar to TDDFT in spirit. Both are response theories, and both use so-called Dyson equations, even though typically in TDDFT that's a little bit more implicit. But the Casida equations, which many of you will know, that's essentially just a Dyson equation for two-particle response function in a particle-hole basis. So when we do BSE, we solve the Dyson equation for the two-particle Green's function, which I call here G2. And this object is relatively complicated because it depends on 4 coordinates. And also the kernel of this Dyson equation also depends on 4 coordinates. And this is, well, this equation which basically takes as an input a non-interacting two-particle Green's functions. Let's say a non-interacting particle and non-interacting hole, and turning it into an ensemble of interacting particle-hole pairs. That's called the Bethe-Salpeter equation. That's pretty similar to TDDFT. So in TDDFT, we also have a Dyson equation, but there we only look at the density-density response. And the density-density response is easier to solve for than for the two-particle Green's function, because it only depends on 2 variables. Well, TDDFT has some issues. These are 3 which are kind of relevant to the description of excited states. So there's a wrong asymptotic behavior of the exchange correlation potential, right? So we do not decay as 1 over R. And this typically leads to an incorrect description of charge transfer states. And, well, closely related to, I mean, they're all closely related, right? And typically we have also massively underestimated fundamental gaps. But fundamental gaps, they are kind of like our first order starting point for excitations. And yeah, so these issues combined, they make it sometimes problematic to actually do TDDFT. Well, you can do TDDFT, but makes it sometimes a little bit inaccurate in practice, and there are ways around it. For instance, range-separated hybrids, or range-separated double hybrids, if you like. But BSE solves these problems a little bit more directly. So typically what we do when we do a BSE calculation, we start with a GW approximation. So the GW approximation, it basically consists of 4 coupled equations. So the first equation here defines a self-energy. And you see here the Hartree term, just the normal Hartree potential, and then you see the GW. That's why the GW approximation is called GW approximation. And then you can expand further in this parameter called W, which is a screened interaction. So we actually in ADF, we also, if you like, you can also take into account the term of second order in W. There's only one, that's quite convenient, but I'm not going to talk about that today. So the W is also obtained from a Dyson equation. And the kernel of this Dyson equation, the P, is called the polarizability. The polarizability, well, that depends on the Green's function, and the Green's function itself depends on the self-energy. So this is a self-consistency loop. And it's quite cumbersome to solve this. So in practice, we simplify the last equation to make the self-consistency a little bit easier. And in practice, there are basically three flavors of GW which are used. So the first one is G0W0. G0W0 basically says we only calculate the diagonal elements of the self-energy. That's very convenient because then we actually do not need to solve anything consistently anymore, right? So when we have, because the off-diagonal elements of the self-energy won't change, so they are just staying at the TFT level. And we basically just calculate a perturbative correction to our first order, typically DFT energies, as you see in that equation there on the left. Then we can also go a little bit further and we can say, okay, we calculate our perturbative correction to our Kohn-Sham eigenvalues, and then we take those again as a starting point and calculate again the perturbative correction and so on until self-consistency is reached. This is called eigenvalue-only self-consistent GW. And then you can also do quasi-particle self-consistent GW, which is typically abbreviated as qsGW. And here you iterate eigenvalues and orbitals until self-consistency. Quasi-particle self-consistent GW is not completely self-consistent GW because the self-energy is actually non-Hermitian. And in quasi-particle self-consistent GW, you only consider a Hermitian form of the self-energy. But as you see on the right, I made a very nice graph where you basically see for these three approaches the starting point dependence, so the dependence on the Kohn-Sham orbitals with which you start your calculations, and you see the computational cost. And G0W0 has a very strong starting point dependence, but of course it's also cheaper because we don't need to do it self-consistently. And the other two approaches, they have a very reduced starting point dependence. In fact, quasi-particle self-consistent GW is completely starting point independent because you also update the orbitals, right? And actually the computational cost, if you implement it in a clever way, is actually the same in both approaches. And yeah, well, that's enough theory, right? So what can you calculate? So by now we have quite lots of functionality implemented in AMS. So of course you can calculate quasi-particle energies, which are related to ionization potentials, electron affinities, homolumo gaps. And for instance, that can be used actually with my former colleague Jelena. We have a paper where we actually applied this to calculate redox potentials, which are related to the ionization potentials. And then, of course, you can model excited states using BSE based on GW. You get excitation energies, oscillator strengths, lifetimes, spectra. The same what you typically get from TDDFT. We can also use that formalism to calculate ground state energies. That's typically called RPA. And then we can also make RPA more accurate by using so-called second order screened exchange corrections. And with quasi-particle self-consistent GW, you can also do things like population analysis, Mulliken population analysis. You can do a symmetry adapted fragment orbital analysis, all those things which you can also do with DFT. All this functionality is supported at all levels of self-consistency. And in the upcoming release, we also support spin-orbit coupling with a true two-component implementation, also for all of this. So just to give you an example, what you how accurate it is. So we calculated, for instance, here the quasi-particle energies of organic acceptor molecules. That's a comparison to a coupled cluster for different flavors of GW. On the left, ionization potentials, on the right, fundamental gaps. And I mean, these molecules are very nicely behaved, what you would typically call weakly correlated. But you see that quasi-particle self-consistent GW gives you a mean absolute deviation of only 0.09, so 0.1 eV. That's great. And also it gives you great fundamental gaps. And actually now when you look at G0W0 results based on two different starting points, so the at typically indicates a starting point, you see quite different results. What else can you do? Well, now moving on to BSE, we have recently also calculated some excited states of chlorophyll monomers and dimers. And so you see here in these tables, comparison to experiment. So most relevant comparison is here the vertical excitation energy, VEE, because that's what we calculate in our linear response calculations, and we do not take into account any vibrational effects. And you see that especially quasi-particle self-consistent GW is very close to the vertical excitation energies, but also eigenvalue only self-consistent GW. And while these range-separated hybrid functionals, well, it depends a little bit which one you use, right? Sometimes they work very well, sometimes they do not work that well. All right, and finally, before that, a little bit about the performance. So as Fedor mentioned in the beginning, one of the main points of our implementation is that we try to be fast. And GW is slower than DFT, and BSE is also slower than TDDFT when you work with GGAs. When you work with hybrid, it's actually not that much slower. It's more or less the same speed. So we recently calculated the lowest 12 excited states of a 6-chromophore model of photosystem 2. It's around 2000 electrons. And it took around 5 days on one node. So I admit it was a very modern node, had a 64 cores and lots of memory. But we also used a large basis set. So you see our largest calculation, we used more than 10,000 basis functions. And yeah. So yeah, if you compare the timings for BSE to the range-separated hybrid, here in this example, omega B97X, with the same basis set, you are not much slower. Finally, ground state energies. So I mentioned there are like different variants of RPA and also second order screened exchange. You can think of it a little bit like MP2, but a little bit smarter. So there are no divergences for small band gaps or large systems, and typically you get higher accuracy. And here I'm just showing some results for ionization potentials, electron affinities, and barriers. And especially for ionization potentials, electron affinities, you get, these are just delta SCF calculations. So in those delta SCF calculations, you get actually great accuracy. And these accuracies, I mean, you might get them with double hybrids, but especially when you use second order exchange, you really get good results. You don't really get great results for everything you see here for the barrier heights. Actually, RPA works very well. The second order screened exchange makes things worse. But yeah, that's a different issue. All right. Now I'm going to demo something, and this is a singlet triplet gap of benzene. So, so that's for now the last slide, and then I'm going to actually demonstrate a few calculations. So, well, benzene is, of course, everyone likes it. It's quite important prototype system because it's aromatic, and yeah. In the singlet triplet gap, what I call singlet triplet gap is the energy difference between the ground state S0 and the lowest excited triplet state. And of course, in practice, this to calculate a singlet triplet gap, you have like vibrational effects, you have geometry relaxation, and that is something we do not take into account, and it's also something we cannot take into account yet at the BSE level. But I'm going to demo that you can actually get great results with BSE at GW compared to experiment. And the reason for that is a little bit that when you neglect the vibrational effects and the geometry relaxation, you typically get quite a nice error cancellation. And Yeah, so let's get started. I stop sharing this and actually share again my desktop. So you should now be able to see the GW in case
yeah,
you don't.
We can see it.
Okay, great, thanks. So I already copy pasted the coordinate of the benzene molecule inside. And now I'm basically just going to show you how you can get a good result for the system, like what settings are important, etc. So first of all, the functional. I mentioned that there's a strong starting point dependence on our functionals. And typically what works best, if we now restrict ourselves to G0W0 at first. You should do a hybrid. I typically like to use PBE0. And then in our experience, so what it is typically known that 40 to 50% of exact exchange works best. You can simply tweak that here. And so now basically we're going to do a calculation based on PBE0 with 40% exact exchange. Relativity we can switch off, but doesn't matter. I could also leave it turned on. TZ2P is a good basis set. And so typically now we are looking at, I'm gonna show you excitation energy. So typically they converge quite fast with respect to the basis set. TZ2P is typically sufficient. So you don't need to do quadruple theta, etc. That's a little bit different for quasi-particle energies where you typically need to go really large. Very important, we turn off frozen cores. That typically doesn't save you much in your calculations in terms of computational time, but it can make your results really worse. So we switch that off. Numerical quality, I like to go to good. I mean, this for TZ2P, you can also do normal for a small molecule, but in general, good. And if you can afford it, very good. That's typically great. And to switch on BSE, you just go here to the excitations panel. Now we are only interested in triplet excitation, so triplet only. And here we turn on BSE. I only care about the lowest excited state. Yeah, BSE you see in the drop down, there's Davidson and BSE. So BSE uses a Davidson algorithm typically. You can actually also do an exact diagonalization, but yeah, I'm not gonna show this. So yeah, and now I could in principle just save this calculation somewhere. Yeah, of course I did run this before, and I could run it now here, but then that would now take a little bit of time because my laptop is not that powerful, and the ADF needs to compete with Zoom for the computational power. So that will take some time, and that's why I'm gonna go to our remote cluster actually. So and I will basically now stop working with the GUI and just submit the calculation there, because then I can demo more stuff, which is nice, I guess. So I go to the terminal, which I hope you see again. I open this input file. These are just the coordinates of benzene you're seeing here. And the settings I just discussed. So you see TZ2B basis, no frozen core. We use our PBE0 with 40% exact exchange. That's what this means. And we care about the lowest triplet excitation. BSE is yes. If BSE would be no, you would just do a normal TDDFT calculation. Okay, and now I submit this and hope that the queue is empty. It is great. And let us look at the log file. That whole calculation should take a little bit less than a minute. So now we are calculating integrals. We are doing an SCF. Well, that is just a hybrid calculation. That's very fast for this system. And now we start the GW calculation. That should take a few seconds. And yeah, we wait a little bit. And then you see here our quasi-particle energy. So we have a HOMO energy of 9.9. So yeah, the ionization potential is minus the HOMO, so 9 eV, the LUMO is 1.8, and a HOMO-LUMO gap of roughly 11 eV. By now, the excitation calculation has started, so the Davidson is working. You see a few cycles. Typically, for such a small system, it will convert. Oh, we already converged, great. And let's look at the output file. All right. We'll just go to the end of the calculation, and we look at the result. And here is our energy, our final singlet triplet excitation energy, our singlet triplet gap. And you see we have 3.64 eV. And in case you might remember that what I showed on the slide here, the experiment is 3.66, right? So we are incredibly close with 3.64. Well, now I'm going to show you what happens if we, first I'm going to make this result worse. That's super easy. To make a result worse of a G0W0 calculation, you just need to use a horrible starting point. And a very bad starting point actually is PBE. And often actually you will see in the literature that people use PBE for G0W0, and that's basically just because, well, it has been typically done in solid state calculations years ago, and there it also works better. But for finite systems, it's really terrible. You will get massively underestimated quasi-particle energies, because G0W0 typically inherits the problem of the underlying DFT functional. So PBE gives you massively underestimated gap, and G0W0 actually started doing a great job to correct for that. But since the gap with which you start is not that great, yeah, it cannot correct for everything. So you see we have here a HOMO-LUMO gap of 10.3. Before we had a HOMO-LUMO gap of 10.9, so 0.6 eV difference in the HOMO-LUMO gap just by changing the starting point. And you will see soon that this also, well, translates into problems with the excitation energy. We won't get a good singlet triplet gap now. So that's often kind of a problem of GW calculations in practice. When you do G0W0, you kind of need to know what works well. It's a little bit like this DFT, right? So let's look at the result. We go to the end of the output, and we see we have a singlet triplet excitation energy of 3.29. So that's 0.4 below the experiment. So that's not great. So what can we do about that? So I mentioned that we can do kind of self-consistency, which helps us to overcome the starting point dependence. And I do this here now in the text. That's the text editor. That's very easy. So you can then switch on the GW block, and there you have lots of options what you can do. You do self-consistency evGW. That will iterate the eigenvalues, but not the density. So again, we do PBE, and changing the title. So everything else is the same, right? We just now do self-consistency in the GW. It will take a little bit longer now, but it's quite interesting to see what actually is going on here now. So again, well, we are going to do our PBE calculation. And now soon we are going to start the self-consistent GW calculation. So now we do our first iteration as before. And yeah, we wait a little bit. So yeah, that's our first iteration. And you might remember the first iteration of a eigenvalue only self-consistent GW calculation is just exactly a G0W0 calculation. So the HOMO-LUMO gap here is exactly the same as in our, no, not this one, this one, in our previous calculation. So that was the result of our G0W0 calculation based on PBE. And that's the first iteration of G0W0. Of the eigenvalue only self-consistent GW. It's exactly the same. And now you see that we converge actually quite quickly. So the HOMO-LUMO gap makes a big jump. We are already, after the first iteration, or after the second iteration, we are already quite far. You see on the left the change in the HOMO energy, which we use to measure the error of those calculations with respect to the previous calculation. And you see you essentially converged after 5 to 6 iterations. We use some DIAS, what typically something you would also use for your normal DFT calculations. And so that typically converges quite fast. So here we are. And now again, we calculate our excitation energy. So you see our final HOMO-LUMO gap is 11.14, right? So before with G0W0, we had, again the wrong one, 11.3. So we almost changed the HOMO-LUMO gap by 1 EV when we do eigenvalue only self-consistency. And the price which has to be paid is, of course, the self-consistency cycle you see here. An iteration takes around 15 seconds. So now we have 6 of those. So that's 90 seconds instead of 15. All right, we are done again. Let's look at the output. Let's look at the singlet triplet excitation energy, 3.44. So what did we have before? It was this one, right? So this one on the left is G0W0, 3.3. On the right, eigenvalue only self-consistent based on PBE, 3.44. So essentially we have improved our singlet triplet gap by 0.15 EV. But again, we are looking for 3.66. So we are a little bit below. So eigenvalue only self-consistency is typically great to fix your HOMO-LUMO gap and your quasi-particle energies, but the orbitals are still wrong. And of course, the orbitals, they also heavily influence the outcome of your excited state calculation. And eigenvalue only self-consistent GW can't do anything about that. So now I'm going to do a quasi-particle self-consistent GW calculation. And I basically just exchange EV by QS. And now we will also update the orbitals. Sorry, I will just change the name of the output file also. And just saying, I mean, I could have done exactly the same in the GUI. I'm myself not a big GUI user, but it's actually, I don't know. Actually, I learned to use it for this webinar. And it's super amazing how fast I could learn it. So it's really great. All right, that will basically now take the same time as the eigenvalue only self-consistent GW calculation. And that's also the last calculation I will demo. And then we can answer questions. So note that here we also use PBE as starting point, right? So only that now we also update the orbital energies. So that's a different to the eigenvalue only self-consistent GW. And well, you won't be surprised if I tell you that I already know the result. So spoiler alert, the result will be better. And this is because quasi-particle self-consistent GW is actually, it is kind of a very fundamental theory. And the people who invented this method around 15 years ago, Cortani, Van Schifka, de Valère, they could actually prove that quasi-particle self-consistent GW is better than fully self-consistent GW, because I showed you in the beginning the self-energy, you neglect all these higher order terms when you do GW. And by neglecting the, or by approximating the emission self-energy as emission, there's actually, it's not even that hard, this proof. You will, you kind of cancel the effect of the higher order term. So you get a, well, you get a quite good error cancellation. Yeah, so typically, yeah, it's actually astonishing how well it works in practice. So you see here on the right, in the self-consistency, the weights of the DIAS, and you see that it converges very fast. That's the weight of the latest state. So we are typically at around 1, and now we are going a little bit lower. So typically we are looking for something below 0.5 at self-consistency. And if your self-consistency cycle stops at, for some reason, at something like 0.9, 0.8, that will typically be a sign that you're not converged yet. So typically you should be rather at something 0.3, 0.4 in practice. And you see here also the density. Well, the density is now changing as well, and you see the difference in the norm of the density with respect to the latest to the previous iteration. So you see that drops quite rapidly, and now basically our energies and our density are almost converged. We are at 8 iterations, now we are at 9, we are converged. And again, now we are doing our excited state calculation. Yeah, and as I said before, this is completely independent of the starting point. If I would have started from B through lib instead of PBE, I would get exactly the same result, depending, of course, on my convergence criteria. We are converged. All right, let's look at the result. And well, perfect, 3.66 eV, right? So that's, of course, what we were looking for. And well, that is, of course, quite fortunate. I mean, in practice, you cannot expect to reproduce experimental results without any error. That is, I guess that's clear. But that just shows you how things work. And yeah, that they can actually work very well. Just a summary of the of what I just said. Practical considerations. So if you do G0W not choose the right starting point, it is important that you use a hybrid functional with 40 to 50% of exact exchange. You can use B half and half lib. You can also use a range separated hybrid. They work great as well. But it typically doesn't matter what you use as long as you have enough exchange. And do not use PBE and do not use LDA. That is something what has been done in the solid state literature early on. It works quite well for solids. It doesn't work well for molecules. Self-consistency reduces this issue. Typically 6 to 8 iterations are required. Quasi-particle self-consistent GW is best for high precision. Typically you need quite higher requirements in numerical settings when you go to larger molecules. And eigenvalue only self-consistent GW is a useful alternative, especially when you look at quasi-particle energies. But I typically do not trust it that much for BSE. For BSE, I really recommend G0W not based with a hybrid starting point or quasi-particle self-consistent GW, if you can afford it. Basis sets. So for DFT, you are typically used to, let's say, TZP is good enough, and QZ quadruple theta is not really needed. And if you look at individual quasi-particle energies, you have the problem that they converge very slowly to the complete basis set limit. And if you really want a good, accurate ionization potential for the right reason, so without any basis set errors, I recommend to do a triple theta and a quadruple theta calculation and then extrapolate. Because even with quadruple theta, you will typically be around 0.1, 0.2 eV away from the right answer. For BSE, the only thing what enters the BSE Hamiltonian are quasi-particle energy differences. And those converge very nicely typically with the basis set. So I showed you here TZ2P, and that is typically sufficient. If you go to quadruple theta, you will typically lower your excitation energies by a little bit, but typically only a few 10 milli eV. And numerical quality, to be safe, I recommend to use good or even very good. Very good is very expensive. Well, typically twice as expensive as good. So I would go for good. And for BSE, something you can do, you can also just use a subset of transitions. There we have a key that's called modify excitations. And there you can basically decide I only want to consider orbital energy differences within, let's say, 2 Hartree, 3 Hartree. That typically won't change your final result if you're just looking at the lowest excited states. But in problematic cases where your Davidson doesn't converge, that always helps. Well, as a summary of what I just said, I just summarized all these values we just calculated for the singlet triplet gap of benzene. Sorry. So we have our experimental value of 3.66. And here for comparison, I show you this DLPNO, CZSTT, delta as delta, as a difference of the singlet and the triplet calculation. taking into account 0-point energy renormalization. So they do everything right in this calculation. So no error cancellation, you get 3.76 eV, which is of course, yeah, that's great. And now all these BSE and GW calculations. So 3.64 with G0W0 based on PBE0, 40% exact exchange, which is great. Much worse result when you start from PBE, you're away by 0.4 eV. Eigenvalue only self-consistency improves it again. And quasi-particles have consistent GW much better. Perfect agreement with experiment. And in fact, you more or less get the same result as PBE0 with 30% exchange. That's pretty general. I mean, I'm quite surprised. I looked at that quite often, and PBE0 is 40% exact exchange for like medium-sized molecules, typically gives you the same result as quasi-particle self-consistent GW. Of course, you cannot always count on it. It might be different for larger molecules. You might need smaller amounts of exact exchange. And if I didn't show that yet, or didn't show that today, but if you would do the same calculation with PBE as a starting point and not with PBE0, you would also get 3.66 eV. So bottom line, if you do quasi-particle self-consistent GW, you don't need to worry at all about your starting point. All right, I guess that was my last slide. That is a backup slide. I think that's not interesting. I'm going to talk about this one. So yeah, that's the last slide. I'm gonna stop screen sharing now, I guess, and yeah, well, I stay in the share, I don't know. Well, in any case, I'm looking forward to answer your questions.
Okay, thank you, Arno. Very instructive series of calculations here. I don't see any questions in the chat, so if people have questions, let me enable unmuting yourself. So yeah, please, if there's any questions from the audience, now would be a good time. Of course, you can always send us questions later on via email if you have time to digest all of this.
Yeah, obviously I talked way too much, so I can understand if I already answered all of your questions.
All right, so now if somebody wants to ask a question, it's possible to unmute yourself. So it should be possible at least. So. Well, while people are gathering their thoughts, maybe I can ask a question. So the slide where you showed where you have G0W0 and you have evGW and qsGW, you showed that the computational cost actually is sort of the same for eigenvalue consistent and quasi-particle consistent. Yes. But I guess the additional hidden cost there is that for qsGW you need higher accuracy. Is that understanding correct?
Yeah, you're completely right. So if you would keep all the technical parameters the same, you get the same cost. But indeed, so typically with quasi-particle self-consistent GW, I mean, if you go to a system, let's say 100 atoms, I typically feel safer to set the numerical quality to very good, while with evGW, I'm very comfortable with staying at good. And that typically gives you a factor of 2. It's not always like this, but yeah, indeed, there's a tendency.
But yeah, so I guess the advantage then is if you can afford it, qsGW is a little bit more well, idiot-proof, if you will, right? So you don't need to make sure that you have the right amount of exact exchange to begin with.
Indeed.
Okay, that's clear.
Idiot-proof, like, I mean, completely ab initio, if you like. So no empirical parameters entering the results.
Right, and so I guess, yeah, whenever you can afford it, you want to go with quasi-particle self-consistent GW, also in combination with BSE for excited state properties. Are there any counterexamples where BSE actually qsGW BSE would do worse than DFT, TD-DFT, or is it always going to be the best option?
Honestly, I I cannot think of any example where this goes wrong. I mean, there will be many examples, of course, where a TDD-FT calculation with some functional will give you a better result as a BSE calculation, but you typically do not know before you try different functionals. I mean, there are some nice ways. For instance, when you do like a TDD-FT calculation using a range-separated hybrid, where you can tune your range separation parameter. I mean, you can also, we have a very nice script actually in AMS. You can do this, and this is typically also great, but it is also not much cheaper than BSE. That's why I wouldn't know any system where I would say don't use it. TDD-FT is better.
Understood. Good. Okay, so that's a clear message. And so BSE currently is available in the development snapshots, right? So if people want to use that, yeah, they should probably let us know. And I take it you will be happy to receive any feedback on people using that in practice.
I would be super happy. I mean, so far, I mean, it was mostly me who used it and Eric. I should say one thing, which I just had to follow up to what I just said. And actually, there are many reasons why it might actually make sense to use TDD-FT right now. And that is when you look at molecules in solution, for instance, because right now, I should have mentioned that, I forgot. BSE, we cannot take into account environment effects at BSE yet. That's something we are starting to work on at the moment. But right now, yeah, you cannot do it. And of course, you can do that at the TDD-FT level. And if you have a molecule in solution and you cannot take into account the environment via, I don't know, at least Cosmo, but ideally, I don't know, using some QUMMM, the most accurate vertical excitation energy won't help you because your result will be wrong. And
got it. Yeah.
Please keep using TDD-FT, don't use BSE. But maybe next year you can also use BSE for that, I hope.
Okay, good. Well, we will invite you for another webinar then. So in the meantime, there's a question from the audience. And so first of all, thank you for a nice and informative talk. Does BSE account only for single excitations, or can you also take into account double excitations?
Yeah, great question. Very important in practice, indeed. But no, you cannot. Well, yes and no. So in the BSE approach, which I just showed you, as it is implemented now, BSE cannot account for double excitations. However, let me go to the slide with the kernel. So this equation where this K1, 2, 3, 4 is the functional derivative of the sigma with respect to n, where, by the way, n is a typo, it should be a g. So this is actually in practice adiabatic kernel, so it depends on frequency, but typically we neglect the frequency dependence. And if we would keep the frequency dependence, then BSE can actually account for double excitations. It is not implemented, but it's actually also something we are looking at. It would make the calculations more expensive though. So short answer, in principle, BSE can in our implementation, and as it is implemented essentially in all codes, it cannot.
Okay, so again, maybe something for a future topic for a web presentation then. And yeah, I can imagine that having nice applications as well.
Yeah, exactly.
Good. Okay, let me see if there's any other questions. So please, if there's anybody from the audience who has any other questions to Arno. Well, if not, let's wrap up for now, and thank Arno again. Thank you, Arno, for this very instructive presentation and set of demonstrations.
It was fun.
And yeah.
A question.
Good. Okay. Well, thank you, everyone, and yeah, hope to see you at the next webinar.
All right, then I'm also gonna leave, I guess.
Yeah. Okay. Thank you, Arno.
All right.